Time before we get to our main event this morning. So welcome to FHPC 2015. I'm Jeff Manlin, this is TR Rumpf. So just a few notes before we get to our main event of the morning. So the chair's report will occur, just to remind you, during the last paper session. So there'll be one paper and then we'll do the chair's report. So for the concluding discussion after the tea break is from 4 to 4:30 p.m. We'll be talking about the future of FHPC, and for that we'll be soliciting some lightning talks. The idea is these are 5-minute talks, 2 to 3 slides, what you think the future of FHPC should be. So please coordinate with either me or TARC. We'll try to collect those slides together so we can turn over the lightning talks very quickly. So possible topics include, what are the important problems that our community should be working on? What are the important benchmarks that we should all be using? How can we better coordinate or collaborate with each other? And how can we attract a broader audience to FHPC? So functional programming is great. I hope everyone in the room agrees with me, but there are lots of people who do things that are not just functional programming and certainly not just Haskell, and we want those people to be part of our community too. So how can we encourage them to be part of this group here next year? So I think we have a great program, an exciting program ahead of us, including the main event, which is just about to occur now of the morning. And TARC will do the introductions for me. Thank you.
All right, and with that, it's my great pleasure to introduce our keynote speaker, Milind Kulkarni. Milind got his PhD from Cornell working with Keshav Pingali, and then he was a postdoc at UT Austin, and in 2009 he joined the electrical engineering and computer engineering department at Purdue University. And just off this semester, he's a tenured associate professor. So Milind has been doing exciting work, which is very relevant to this community here, which is about analysis and transformations for recursive, irregular applications. And I'm grateful to Milind that he agreed to speak here, and I think it's your first ICFP, right?
It is my first ICFP, yeah.
Yeah, so it's a great opportunity for the ICFP community to learn about this exciting work.
Yeah, so
okay, the floor is yours.
Thanks, TARC. So speaking of broadening the community, I'm really not a functional programming guy. I do a lot of work in optimizing compilers. And I think, hopefully, that as I talk about the kinds of stuff that we've been doing in our group for the last 4 or 5 years, some of these things will start to smell familiar to you guys. I think there's actually a lot of commonalities between the kinds of stuff that we do, the kinds of transformations that we do, the kinds of analyses we're worried about, the kinds of applications we're looking at, and the kinds of things that people in the functional community have been thinking about for a very long time. And so I hope to foster a lot of discussion and hopefully some new collaborations and connections and things like that. But what I want to tell you about today is, like I said, stuff that we've been doing in my group for the past 4 or 5 years. And I gave it this talk, titled Regularizing the Irregular, but fundamentally what we're looking at is, can we take recursive, irregular applications and optimize them in various ways? Can we parallelize them? Can we improve their locality? Can we transform them to get better performance? And so I come at this from a very compiler-centric, sort of traditional optimizing compiler background, where in the compiler community, the world of polyhedral framework and unimodular transformations and stuff like that, we know a lot about what we can do with regular applications. These are applications that deal with arrays and matrices and the like, and so we've developed tons and tons of transformations for them: loop interchange, loop tiling, loop skewing, loop reversal, et cetera, et cetera, et cetera. And lots of analyses that tell us when these transformations are sound, that tell us when these transformations might be effective, and things like that. But if you step away from regular programs, from matrices, from arrays, from the kinds of stuff that you see in dense linear algebra, we really know a lot less. So there's been some work, for example, by Michelle Strout here, on looking at sparse matrices, but there's basically just not been nearly as much work at looking at these irregular applications. And when I define irregular applications, what I really mean, from my perspective, are programs that operate over pointer-based data structures: trees, graphs, lists, and the like. And the fundamental problem here, the reason why this is hard, is that irregular applications are complex in a very particular way that makes it hard for compilers to reason about them. Compilers are able to reason about regular programs, dense linear algebra kinds of programs, because the way that programs access the arrays and the matrices, they use these nice affine index expressions and things like that, and we can do lots of analysis of how those index expressions interact, identify dependencies, figure out the structure of dependencies and things like that. But when we start talking about chasing pointers through trees and graphs, everything becomes very input dependent, it becomes very unpredictable. There's just not as much stuff that we can do at compile time to reason about the way a program behaves, to reason about how we might want to transform a program in order to improve its performance. Okay? And so it's possibly even an open question about whether there are just common opportunities in irregular programs. Are there even a sort of a class of transformations or a broad class of programs that we can attack in some common way, or are we going to be stuck doing a lot of ad hoc kinds of transformations, take a new application, do a new set of transformations and things like that. So my research has basically been about finding common ground. Looking for that common ground, looking for those common opportunities for doing transformations and analyses for irregular programs. And in particular, we've been targeting recursive traversal applications, and I'll give you a quick example of one of those on the next slide. And so what I want to talk to you about today are a bunch of things that we've been looking at, a couple of transformations, one called point blocking, one called traversal splicing. I want to tell you about some very recent work we had on analyzing these kinds of recursive traversal applications to decide when transformations are legal. And then I'll tell you a little bit about various kinds of vectorization transformations and optimizations we've been looking at for these types of applications. But the common pattern here, the key insight behind all of this work is that even though these recursive traversal applications look very irregular and very data dependent, very input dependent, they still actually have a lot of regular patterns that we can exploit in systematic ways. Right? They look very complicated, they look very unpredictable, but in reality, when you actually sit down and look at the way these applications run, there's a lot of common behavior. There's a lot of actually fairly regular behavior that we can exploit. So let me start by telling you about what one of these applications looks like. So this is an application called point correlation. It's a data mining algorithm. And the idea is fairly simple. I've got some set of points in space, so here's 6 points in a two-dimensional space, and I've got other points, for example, this little blue point here, and I just want to look through this space and find all the points in the space that are within some radius r of this point. Right? So this basically gives me some measure of how clustered the data is, right? How close together points are, because the more points that are within a radius r of different points, the more clustered the data is. And the naive approach, sort of the standard way that you might write this if you were maybe a freshman, is you would just take P and compare it against all the other points, right? This is pretty easy. I just enumerate, I iterate through all the points, compare P to those points, calculate the radius, and see whether or not it's within the radius. The problem is that this is really slow. If I'm talking about doing this kind of operation over millions or billions of points, and I've basically given myself an n-squared algorithm. For every point, I need to compare to every other point, right? Think about the way you might do an n-squared n-body algorithm, right? Those of you that are familiar with n-body algorithms know that you often don't do the n-squared algorithm. What you do instead is you use a spatial data structure that captures the sort of spatial locality of these points and use that to accelerate the process of figuring out who's nearby whom. Right? So in the case of something like Barnes Hut, you might use an octree. In the case of point correlation, people can use a data structure called a KD tree. And the way it works is this. I build my KD tree by just recursively subdividing my space over and over and over again, until I wind up with a tree structure where each interior node of the tree represents some subspace, and each leaf node represents a subspace that only has one point in it. And now, when I want to figure out who is near a particular point, I can perform this operation by traversing the tree rather than comparing to every point. So I can start at the subspace A and ask whether this circle intersects this box, and it does. So that means that there's a chance that there's some points in the subspace that are close to me. So I'll just traverse through the tree. So I'll go down to B. The subspace that represented by B doesn't actually intersect that circle. I know there's no chance that any of those points can be in the circle, so I can just prune that entire subspace and essentially just not search half of the space. Right? So I'm able to prune huge chunks of the space by using this tree. So as I work my way down the tree, every time the square or the rectangle intersects the circle, I keep traversing. Once I get down to a leaf node, I compare against the actual point to see whether I'm within the radius, and so on. Right? Now, sometimes I get this wrong. Sometimes the circle intersects the box, but the point isn't actually within the circle, but no big deal. The basic idea is that by using this KD tree, by using this spatial acceleration structure, I'm able to prune off most of the search space and essentially turn what used to be an n-squared algorithm, comparing every point to every other point, into an n log n algorithm. Right? Every point does a traversal of this tree. And two-point correlation is actually a simple enough algorithm that you can show the entire thing on a single slide. Basically, I have my KD tree. I can't really show you that. That's complicated. But once I have the KD tree, I take each point, and I just recursively traverse the tree. Each point checks to see whether it's too far from the current cell, from the current node. If it is, I return. I stop traversing that subtree. Otherwise, if I'm a leaf, I check against the point inside the node. Otherwise, I just continue recursing through the tree. And it turns out lots and lots and lots of algorithms have this basic pattern, where I have some recursive traversal of some recursive data structure, a tree, and I do it over and over and over again. So two-point correlation does this, Barnes-Hut does this, algorithms for ray tracing do this, algorithms for a lot of data mining algorithms do this, nearest neighbor algorithms do this. This is a very common pattern that arises in lots of applications. This idea of doing repeated recursive traversals of recursive structures. So this was the first thing that we sort of started looking at. We said, hey, can we take applications that fall into this particular box, into this category, and do something to improve their performance? Because they are highly irregular. Those data structures, those trees, are very input dependent. The particular traversal that you do of the tree, the particular traversal any point does of that tree, is very data dependent because the test is based on data inside the point. So basically every traversal looks different from every other traversal. It's very input dependent, very data dependent. So can we do anything to improve their performance? So it's hard to reason about these irregular traversal applications because of the pointer chasing I do through the tree and the recursion that I use to traverse the tree. So what I'm going to do, or what we did, is we just ignored it. We said, let's just not pay attention to any of that recursion, any of that pointer chasing. Because in reality, all that recursion and pointer chasing is doing is telling me which parts of the tree I'm supposed to touch. Right? The goal of those recursive calls down there is just to say, hey, you need to look at more of the tree. Right? So let's just assume that we already knew. Let's assume for every point we had some oracle that just told us, hey, for this point, these are the tree nodes you need to touch. You need to touch A, B, C, and D. Some other guy might need to touch A, B, E, and F, and so on. Right? So I just have this oracle. I've abstracted away, hidden away all of the recursion and pointer chasing inside that oracle. So now my new algorithm looks really simple. It's this little doubly nested loop. For each point, ask the oracle what tree nodes you're supposed to interact with, and then go off and interact with them. Do whatever accesses you want. And now that I have a doubly nested loop, I can start deploying some of the techniques, some of the technology, some of the ideas from regular compilers to start reasoning about the behavior of these programs. And in particular, the one that I'm going to use is the idea of an iteration space. I have a doubly nested loop where I'm executing the same code in each iteration. So rather than thinking about that as a single piece of code, I want to think about each instance of that iteration as a different thing, as a different iteration. Right? I basically want to explode out that loop and consider every separate instance as a different entity that I can reason about. So in particular, I can think about having, for each point, so maybe for these 5 points, I can think about the nodes that they might access, and I can basically represent the execution of a program as the execution of a bunch of iterations in this iteration space. Point 1 visits nodes A through G, point 2 visits nodes A, B, and then G, H, I, J, and K, and so on. And I can basically order them, and that tells me what this program is going to do. Right? Point 2, by the way, visits exactly the parts of the tree that we saw in our example. So that's the kind of behavior that you'll see. And once I can explode this out, once I think about this in terms of individual instances rather than the whole loop at a time or rather than all this recursion, I can reason about locality. In particular, I can use reuse distance to think about how good the locality might be in this application. So consider node C. Right? Reuse distance, just to refresh your memory, is basically the number of unique other locations I touch in between the use and the reuse of a particular memory location. So here I'm only considering nodes in the tree. I'm not worrying about anything else. But I can ask, okay, so between the first time I touch C and the second time I touch C, how many other nodes of the tree have I touched? Well, so I can actually basically just look at this graph and say, oh, I touch every other node of the tree before I come back around and touch C. And actually, in the worst case, in general, the reuse distance in an application like this is proportional to the size of the tree. Right? From the time I touch one node to the time I touch that node again, I will have basically touched data proportional to the size of the tree before I get to come back around and see the same part of the tree again. And this is problematic, because the reason we like reuse distance is it tells us something about how good the locality is in our program, and the larger this reuse distance is, the less likely it is that we have good locality. The more likely it is that accesses we're doing become cache misses. Right? And the easy rule of thumb is that if your cache is not big enough to hold at least as many data items as your reuse distance says, so if I can't hold at least 10 items, when I come back around and touch C again, I'm going to get a cache miss. Right? And so this seems pretty bad. Right? Reuse distance is on the order of the size of the tree. When I'm building trees of millions or billions of points, there's basically no hope of getting good locality here. I'm going to get really bad performance. Every single access basically becomes a cache miss. Not so good. So people have played around with this problem before, a lot of it in the context of n-body tree codes. And they said, okay, well, one thing that you can do is you can be a little bit smarter about the order in which you do these traversals, about the order in which you execute these points. Rather than executing the points 1, 2, 3, 4, 5, what I should actually try to do is find traversals that do very similar things and execute them back to back. Because that way I touch less of the tree and there's more reuse from one traversal to the next. So for example, instead of going 1, 2, 3, 4, 5, I could execute 1, 3, 5, 2, 4. Right? So now I've just sort of changed the order in which I execute these points. There's a lot more overlap. And if I now look at the reuse distance of C, the reuse distance of C has gone down from 10, the entire tree, to just 6. So it's more likely that accesses to C become cache hits. Right? What reordering points does is it basically takes your reuse distance from being on the order of the size of the tree to on the order of the size of a traversal. And traversals are much smaller than trees. That's the whole reason we're doing these kinds of tree applications in the first place. I don't have to look at the entire tree. I get to prune off most of the tree. My traversal is much smaller. So I get a smaller reuse distance and hopefully better locality. The problem is that this only gets you so far. As the trees get bigger, as the traversals get larger, or alternately, you can think about if the caches get smaller, I still get really bad behavior. So even after I have these nicely scheduled, nicely sorted points, where points 1 and 3, in fact, do exactly the same thing, right? If my cache is only big enough to hold 4 tree nodes, when I come back around and access C, C will still have been kicked out of cache. I'll still get a cache miss. In fact, I'll basically just get worst case behavior if my traversals are too big to fit in cache. So even after I've done all this sorting, which is non-trivial, but after I've done all this sorting, I still get really bad cache behavior when my inputs get sufficiently large. So what can we do? What can we do about this, right? Can we do better? Can we do better than just saying, well, try to schedule the points in some clever way? So what we're going to do is do a little bit more abstraction. And we'll say that, hey, when those points are sorted, the difference between consecutive traversals is sort of a second order effect. The entire reason we've sorted the points was to basically make consecutive traversals as similar as possible. So let's just pretend that they're the same. Let's stop pretending, or let's stop assuming that traversals from one point to the next are different, and just get rid of that oracle entirely. Let's just assume that different points are doing exactly the same thing. Because once I've sorted the points, those differences become somewhat small from one traversal to the next. So now I have a loop that is basically just a doubly nested loop over 2 vectors, a vector of points and a vector of tree nodes. Right? And for each point, for each tree node, I interact between the point and the tree node. And this has exactly the same locality behavior as a dense linear algebra operation called vector outer product. Right? So I can actually just sort of put this up here. If instead of using for eaches, if I just say, hey, I goes from 0 to the size of the points, j goes from 0 to the size of the tree nodes, interact ps of I, ts of j, locality-wise, that's just like saying a of ij is equal to ps of I times ts of j, which is vector outer product. And vector outer product is one of these dense linear algebra kernels that we know how to optimize, so we know how to get better locality out of. In fact, once we're in this world where we've basically just removed all of the irregularity and all of the sparseness from our abstract model of what's going on, now I can just start reasoning about this code as though it were regular. Okay? For example, I can reason about its misbehavior. I can reason about its cache behavior. So the cache behavior of this program is just like vector outer product. I basically get only cold misses on the points. I bring a point into cache, and then that point visits all of the nodes in the tree, or all of the nodes in this TS vector, and then I never look at it again. So it gets to stay in cache the whole time. Unfortunately, if that TS vector is large, I'm actually going to get a capacity miss on every access to that TS vector, because I access TS of 0, and then by the time I get to come back around and see it again, I've touched everything else in TS. So TS of 0 got kicked out of cache. Right? This is exactly what happens in vector outer product, and this is exactly what happens in tree codes. So what if we start playing around with what we do here? What if you do maybe interchange, right? So put the tree loop on the outside and the point loop on the inside, right? Thinking back to our vector outer product analogy, it actually doesn't help. All you've done is you've traded which vectors have good locality. Now I'm going to get capacity misses on each access to the point and cold misses on each access to the tree, because what this code does is it says, hey, take the first tree node, take the root node of the tree, and have every point interact with that tree node. Then take the next node of the tree and have every point interact with that tree node. right? So the tree now has very good locality, but the points still have bad locality. But of course, interchange is not what people do if they want to get good locality in vector outer product. They do loop tiling. That's sort of the standard transformation that gets done for vector outer product, where I take a block of points, and then for each node of the tree, I have that block of points interact with the node of the tree, and then I move on to the next block of points. And if we take that world and explode it back out to our world of trees, here's what we're saying. Here's what we would like to do to get good locality. I would like to take a block of points, and then ask my oracle, what parts of the tree does that block of points want to visit? For each one of those nodes, have the block of points interact with those nodes. Okay? So I've taken my sort of regular abstraction of what's going on, exploded it back out into my tree world, although I'm still hiding a lot in this oracle. Right? But the basic idea is this. I want to take blocks of points and move them through the tree. This is a transformation we call point blocking because we're taking blocks of points. And it basically looks like this. Hey, take points 1, 3, and 5, have them all visit A. Then take 1, 3, and 5 and have them all go in and visit B. Then all go visit C. When I get to D, 1 and 3 will interact with D. 5 just sort of sits idle because it doesn't need to do any work. It wasn't supposed to interact with D to begin with. I go visit E, G, H. None of the points in 1, 3, and 5 want to go visit I and J, so the oracle would have told us, hey, that's not one of the nodes you have to visit, so I can skip on ahead to K. Right? And then I'll move on to the next block of points, points 2 and 4. And the locality intuition here is actually exactly like the locality intuition for tiling in vector outer product, which is that I'm going to miss on each tree node once per block. Right? Every time a block visits the tree node, I'm going to bring that tree node into cache, but then that tree node gets to stay in cache while I process the entire block of points. Okay? And as long as that block fits in cache, I only get cold misses on the points because I bring the block into cache, the block of points into cache, and then they get to stay in cache the whole time. So I'm going to take these blocks of points and walk them through the tree. This is what we would like to have happen, right? But I sort of hid away a lot of complexity in that oracle traverse function that basically said the oracle is going to tell me what nodes of the tree I'm supposed to touch. But it turns out that we can actually make this work. We can take the actual code and transform it to give us exactly that behavior. And the idea is normally we have this for each point P. Each point then does its recursion, then we move on to the next point P. We want to take that for each loop and push it into the recursion. So what we're going to do is get code that looks like this. Now we're going to talk about blocks of points for each point block P, recurse that entire block of points, and we've pushed the for each into the recursion. So when I call recurse, I say for each point in that block, have the block interact with the tree node. And that red code there is basically exactly the same as the code of the original recursive function. Right? There's only two differences. One is that instead of returning when I'm supposed to truncate, that too far condition, I continue because I need to process the rest of the points in this block. And the other is that instead of making the recursive call immediately in the else block there, I just defer the recursive call until I've processed all the points in the block. So what I've done is I've just pushed the recursion into this code. I defer the recursion, and then once I'm done, I send all of the points in the block to the left node and the right node of the of the tree. Okay? So this is point blocking. It basically gets us much better locality by blocking the points, having blocks of points move through the tree in lockstep. So we did a quick experimental evaluation. The details are not super important, but we looked at 6 different tree benchmarks, and for different inputs, we get different behavior because there is a lot of input dependence here. And here's the final takeaway. The final takeaway is that these inputs are all roughly on the order of 1 million points, and so these numbers actually get better as the inputs get larger and larger and larger. But with inputs on roughly the order of 1 million points, on average, we're getting about a 50% performance improvement through point blocking. Okay. So this was kind of the first thing that we did. We said, hey, let's just do this transformation. It looks a little bit like tiling. It basically is tiling for trees and tiling for irregular programs instead of tiling for matrices. And we get this kind of performance improvement. So the natural question to ask is, hey, when I restructure the code like this, when I change the order in which the traversals happen, is that actually sound? Am I actually breaking the code by doing this transformation? Under what circumstances can I do this transformation? Can I group points together and have them move through the tree simultaneously and make sure that I actually still get the right answer at the end? And originally we said, well, point blocking is sound, so this transformation is sound, as long as different traversals have no dependencies between them. Any individual traversal will still happen in the same order. All we're doing with point blocking is kind of interleaving the traversals. Right? So as long as the traversals don't have any dependence between them, that interleaving isn't going to matter. I'll get the right behavior anyway. Right? But what if the traversals interact? What if there are dependences from one traversal to the next? Can we still do point blocking? And it turns out the answer is yes. Even though I'm restructuring the schedule of execution, even though I'm interleaving the execution of these traversals, point blocking does it in a particular way that doesn't necessarily break the code. So consider, for example, inserting points into a binary search tree, or inserting numbers into a binary search tree. So I can take 10 and insert it into the tree. Then I can take 11 and insert it into the tree. It follows exactly the same path as 10 does, and then it goes and makes itself a child of 10. Right? So that is two consecutive tree traversals. Right? Suppose I wanted to apply point blocking here. Suppose I wanted to make those two tree traversals happen in lockstep, work their way down through the tree simultaneously, which will get me nice locality in this tree, because they both touch the root at the same time, they both touch node 9 at the same time, etc. So even though the traversals interact, point blocking doesn't completely change their order. So what will happen is they both start at the root, and then they work their way down to the tree, through the tree at the same time. 10 gets to add itself, and then 11 sees 10 in the tree, and so can add itself as the right child of 10. Right? So even though there's some interaction between these traversals, what one traversal did to the tree is observed by the second traversal. The interleaving is a little controlled. The write that 10 does still happens before 11 kind of looks at that node. Right? So 10 inserts itself before 11 even really looks to see if 10 is there, and so it actually still works out okay. So what we want to know is, can we come up with a scenario, can we come up with a test that tells us that even in circumstances like this, even when there are dependencies from one traversal to the next, I can still do transformations like point blocking. So to sort of understand why point blocking might still be safe, let's turn back to our iteration space, right? This exploded way of thinking about every separate instance of the program. So here is the generic code for each point, recurse, and the recursion just says if it's a leaf, do some work, otherwise keep recursing. And if I explode this out into an iteration space, I can think about the execution of this program as saying each point does all of its work and then I move on to the next point. Right? And what point blocking does is it just reorients the iteration space. It says now points 1, 2, 3, and 4 all interact with A, then points 1, 2, 3, and 4 all interact with B, and so on. Right? I've changed the order of execution here. What I've done is I've rescheduled the computation. Right? In fact, in the world of regular programs, we often talk about these as scheduling transformations. What I've done is I've rescheduled these iterations, but this rescheduling doesn't actually change the order of every iteration. Some iterations that used to be in a particular order in the original code are still in that order after I apply the transformation. Okay? I have not reordered all of the iterations. I've only reordered some of the iterations. So think of, for example, point 2 visiting node C in the tree. Okay? It turns out that all of the iterations in that blue box there happen after node X, after iteration X, both in the original code and in the point blocked code. In the original code, they all happen after node X, and after I do this transformation, they still all happen after point X. Right? So if I had a dependence that sort of was from iteration X to one of those iterations in that blue box, right? If, say, iteration X wrote to a location and then one of the iterations in the blue box read from the same location, the read would still happen after the write in both the original code and the transformed code. There was a dependence, but nothing broke. The read still saw the correct thing. In fact, the only time I run into trouble is if I think about iteration Y. Iteration Y is point 3 visiting node B. In the original code, everything point 3 does happens after everything point 2 does. Right? But in the transformed code, because point 3 gets to node B before point 2 gets to node C, the order has changed. And when I change this order, if there's a dependence, if point 2 writes to a location when it's at node C, and then point 3 reads from that same location when it's at node B, in the original code, I have a very nice read after write dependence. In the transformed code, the read happens before the write. Not so good. Right? So what we can do is actually come up with a test that captures exactly this circumstance. Right? What this test says is point blocking is safe if, for all iterations, and I'm going to just identify iterations by the point and the node, right? For all iterations, if there's an interference between those two iterations. So that top thing just says they access the same location. And the first point comes before the second point. As long as the first node also comes before the second node, so ni is earlier than nj, everything is okay. Right? So this test basically captures when point blocking is okay. For all iterations, if this is true, then I can apply point blocking, the transformation works, everything is hunky-dory. Now, things are a little bit complicated, and that's because knowing whether ni is before node I is before node j basically has to do with the order in which I traverse the tree. Right? What I'm saying is that in a traversal of this tree, I would get to node I before I got to node j, but that can be a little bit hard to reason about if these two nodes are in very different parts of the tree. How exactly am I traversing the tree? It's hard to say. So what I can do is I can make this test a little bit stronger, a little bit more conservative, and say, well, one thing I know for sure is that ni, node I, is before node j if node I is an ancestor of node j. If node I is an ancestor of node j, then I clearly have to get to node I before I get to go to node j, and so this is just a stronger test. Right? So I'm going to let some opportunities slip through my fingers, but for the most part, I'll capture most circumstances under which point blocking is legal. Importantly, this test allows dependencies. It's not saying that if there's a dependence, you can't do point blocking. It says that if there's a dependence, you can do point blocking as long as the structure of that dependence is okay. So we built something called tree dependence analysis that basically tries to apply this test. It basically analyzes the code of tree traversal programs to apply this test, to try to figure out whether or not the orderings are all fine. And the intuition is that each invocation of this recursive method represents one iteration, one point and node iteration. Right? Every time I invoke this method, I'm invoking it on n and p, so it represents one particular iteration in this code. And so I can run an abstract interpretation that basically gathers what we call rooted access paths. Right? This iteration is happening at a particular node in the tree, and I want to know what parts of the tree can I touch relative to where I currently am in the tree. Am I touching my children? Am I touching my parents? What parts of the node of the tree am I actually touching? Okay? And so if we were to run the access path collection on this, we basically get a bunch of access paths that look like this. For example, at the very beginning of the recursive call, when I'm sitting at node n in the tree, node n is just some arbitrary node in the tree, I read from n.v. Right? And towards the end of the recursive call, if I take some of these conditions, I might write to n.l.v, right? The node's left child's v field. Okay? So I can take these access paths, and now I can apply the dependence test. Right? I want to say for all possible dependencies, this is true. So first I need to figure out which guys are actually accessing the same location. And then I also need to figure out the ordering. So to figure out if they're accessing the same location, what we're basically looking for is whether there's any possibility that those two rooted access paths could collide with each other. Is there some way to instantiate a particular node in the tree? Remember, n is just whatever node I'm currently sitting at. Is there some way to instantiate a particular iteration, a particular node in the tree, so that one of the writes collides with one of the reads, or one of the writes collides with one of the writes? For example, here, I read from n.v and I write to n.v. Well, if I've got two iterations for different points and they're both sitting at exactly the same node in the tree, then one guy is going to read the v field and the other guy is going to write to the v field. So I get a dependence. And then I'm going to look for this OK ordering. And OK ordering here basically just says the prefixes don't violate the ancestry constraint. So n.v and n.v happen when the two nodes are exactly the same. So ni, the first node, is an ancestor or the same as nj, so everything's great. No problem. Right? In this case, the prefixes don't violate the ancestry constraint. But it's not always that good. Right? Take n.v and n.l.v. Here there's a common suffix. There's a way to instantiate the node n so that these two accesses will interfere with each other. They'll touch the same part of the tree. But the prefixes actually do violate the ancestry constraint. And let's see exactly why that is. So suppose n.l.v and n.v collide with each other if some iteration is sitting at node B and writing to its left child's v field. And some other iteration is sitting at node C and reading from the v field. Then there's a collision, right? So this is just instantiating the nodes. So suppose it were the earlier point, pi, that wants to read from c.v, and the later point, pj, that wants to write to b.l.v. What's going to happen, in the original code, the earlier point gets to go in and read c.v, no problem. Then the later point comes in and does it right. But when I apply point blocking, these 2 points are working their way through the tree at the same time. So they both get to node B at the same time. Pj writes to b.l.v, and later, pi goes in and reads from c.v. That breaks things. That violates the ancestry constraint. That says that there's potentially a problem here. I've changed the order of the dependence. Okay, so this piece of code here is actually a snippet of binary search tree insertion, and it just looked like we have a problem here, that I violated this ancestry constraint. The 2 iterations will change their relative order. When I apply point blocking, the code breaks. But at the beginning of this little subsection of the talk, I claimed that it was safe to apply point blocking to binary search tree insertion. So the question is why? And the answer is that these reads and writes don't always happen. These reads and writes are conditional. Sometimes I read from a node n.v. Sometimes I write to n.l.v. I don't always do it. Right? So what we do is a path-sensitive analysis. We actually keep track of the conditions under which these different accesses can occur. So for example, I'm going to write to b.l.v. Pj is going to write to b.l.v whenever b.v is less than pj.v, that's that first condition, and b.l is equal to null. That's the second condition. Those are the conditions under which the write b.l.v occurs. Okay? The conditions under which the read to c.v occurs, that doesn't seem like it helps us much. That actually always happens. If I ever get to node C, I am always going to read from c.v. That's the very first thing I do in the code. But we can be a little bit clever, because I don't always get to node C. I don't always do the recursion. I don't always go from node B down to node C. So what I can do is think about the conditions under which the blue point actually makes its way down to C. I can actually look at the conditions under which the recursion happens, and if I go through the whole process, what I see is that I only even get to node C to read from c.v if either if b.v is less than pi.v and b.l is not equal to null. I can only recurse down to C, the left child of B, if the left child of B is not null. That makes some intuitive sense. I can't obviously go down to a null child. So what I have are these 2 refined conditions under which the dependencies happen. And in these refined conditions, what I can see is I can just ask Z3, and Z3 says, hey, that's not actually possible. Those 2 things can't both happen. The read and the write can't both happen at the same time. You're actually okay. This dependency you thought was a problem is not actually a problem. And so we can put all this together into a tree dependence analysis where we collect all the access path pairs in the program and start ruling them out. We rule out access pairs that have different suffixes. They can never create a dependence. We rule out access pairs that have compatible prefixes. They don't violate the ancestry constraint. And then we use Z3 to rule out accesses that can't happen at the same time. And when we're done, we can say, hey, inserting into a binary search tree is actually a kind of application where I can apply point blocking. And we can do this for a bunch of different kinds of tree building codes, for example, including building Barnes Hut Oct trees. Okay. So we've built point blocking. We've figured out when point blocking is valid. What else can we do? Can we do other kinds of things? Well, something that we looked at recently in our group was, can we vectorize tree traversals? Can we make our tree traversals, can we map our tree traversals to SIMD units? Okay, rather than just running them normally. And there's maybe sort of a natural idea for how you might do this, which is that I've got a bunch of tree traversals that are happening. I've got a bunch of points that are traversing through the tree. Maybe what I can do is assign each point to a different SIMD lane, and then sort of march those points through the tree. Right? Essentially what we're doing, if we do that, is we apply point blocking. So we get a traversal code that looks like this, recurse over a block of points, and then for each point in the block, interact with the current tree node. And then SIMDize this new nice inner for loop that we have. This is a nice dense for loop, so we can SIMDize it, we can vectorize it. And what we've done is we've basically assigned a point to each SIMD lane, and we've walked that group of points through the tree. This actually does not work as well as you might hope. In fact, Pixar tried to use a strategy like this to vectorize one of their ray tracers. And in the paper where they wrote about this, they basically said it doesn't work, so we had to do something else. And the reason it doesn't work is, yes, I'm vectorizing this loop in here. This loop looks like a nice dense loop. But what I did was I picked a bunch of points to put together into a block. And those points might diverge. They might go to different parts of the tree. Right? They're not all going to touch the same parts of the tree. And so what happens is that the block of points becomes sparse. Right? I run out of work that I can do in a SIMD manner. Okay? SIMD is less efficient. I've got lots of unused SIMD lanes. And so I can play some tricks to try to get around this. I could try to use really large blocks instead of putting 4 points together. I could try to put 32 points together and hope that enough of them are doing the same thing that I can still get some useful SIMD. But then I get really large blocks, and that gives me cache misses. So what we really want to do is we want to be able to find traversals that visit the same parts of the tree at the same time, so we can group them together. Can we somehow figure out a way to put together points so that these blocks stay dense? And we do that with a transformation that we call traversal splicing. And traversal splicing is kind of interesting because point blocking said, hey, you've got this for each point, for each node in the tree, do something. And point blocking said, tile the point loop, take a block of points and walk them through the tree. Traversal splicing says, tile the other loop, tile the traversal loop, tile the tree loop. Okay? Take a piece of the tree and walk all the points through that piece of the tree. Then take the next piece of the tree and walk all the points through that piece of the tree, and so on. And what's nice about this, right, this is just a different kind of tiling. It's a little bit harder to implement, but it's basically the same kind of tiling. It gives us an opportunity to do some clever scheduling. So here's how traversal splicing works. First, I'm going to figure out the parts of the tree how I'm going to chop the tree up into pieces. So we call this selecting splice node. So we might cut the tree at a given level. Okay? So here's my iteration space. Then I'm going to execute my code, and I'm going to run up until I get to those splice nodes. Remember, the idea is I'm going to take a piece of the tree and run all the points through that piece of the tree. So I'm going to just run all of the points until I get to the splice nodes. Okay? And now we see something interesting, which is points 1, 3, and 5 made it all the way to node C, but points 2 and 4, their traversals actually truncated before they made it down to node C. They didn't get all the way down to node C. So we actually have some information about the behavior of these points. Now that I've finished processing the first part of the tree, I know that points 1, 3, and 5 have behaved similarly, and points 2 and 4 have behaved differently. So what I can actually do is reorder my points at the splice nodes. Basically, look at the behavior of these points and say, oh, points 1, 3, and 5 all made it to node C. Maybe they're behaving similarly. Maybe I should group them together. So I'll reorder the points and group them together, and then continue on. And now points 1, 3, and 5 get put together into a block instead of points 1, 2, and 3. Okay? So what we're doing is we're basically rescheduling the points as we execute based on how they behave in different portions of the tree. Okay? So the effect is this. We're reordering the points based on their past behavior. And the intuition is that points that behave similarly in the past will probably behave similarly in the future. So we are automatically grouping together points that behave similarly. And if they behave similarly, that means they're touching similar parts of the tree, which means maybe those are good points to put together into a SIMD block. And in fact, that's exactly what we see. This graph is a little bit hard to read because there's a lot of stuff going on here. The main thing I want to point out is the blue bar is SIMD efficiency, SIMD utilization. What percentage of SIMD lanes were we able to effectively use in a given application? And in a lot of cases, it's pretty low. It usually hovers somewhere around 50 to 60%. Right? Meaning somewhere between 40 and 50% of my SIMD lanes are going unused when I just apply point blocking and SIMDize. But once I apply traversal splicing, once I do this dynamic sorting, I get the green bar. And the green bar gives me anywhere from 80 to 100% utilization. Because I'm able to reorder the points on the fly, I'm able to find a bunch of points that are behaving similarly and put them together into a block to vectorize, and that block stays dense for much longer. I get much better vector performance. And so overall, traversal splicing lets us get away with using really small blocks because we're constantly reshuffling what points are in what blocks. And this might sound expensive, but it turns out in practice we can do this pretty efficiently. And so we get very good cache locality, the blocks are small, and we get very good SIMD efficiency because we're constantly rescheduling the points to make sure that points that are together are doing similar things. And so when all is said and done, we can get speedups of sometimes actually more than 4x speedup on 4-way SIMD because we're actually getting good locality as well. And overall, we get somewhere around a 3x speedup on 4-way SIMD by SIMDizing these tree traversals. Okay, one last thing I want to talk about, which is going a little bit more off into left field, but it turns out it's still informed by some of the transformations that we do, which is to push things a little bit further. So I have a long-running collaboration with some people that like to play around with task parallel programming models, languages like X10 and Silk. And so I might have a piece of code that looks kind of like this. I've got foo int x, and then if it's the base case, I do some work. Otherwise, I spawn foo of x minus 1, foo of x minus 2. This probably looks a lot like Fibonacci because it's based on Fibonacci. But this is like one of the classic examples of a silk program, right? And I want to execute these kinds of programs on vector machines. And I found it kind of interesting that Ryan has a paper here talking about converting data parallelism into task parallelism. And we kind of want to go the other way. We want to take the task parallelism that we have and convert it into data parallelism, right? I want to take the naturally task parallel nature of silk programs and expose some data parallelism so I can run them on vector machines, so I can run them on SIMD units. Okay? So, let's start by thinking about what happens if I were to just run this program sequentially. I can think about this program as basically a tree of tasks, right? And each task has children representing the recursive calls, right? So I have a tree of tasks, and normally when I execute this program, I execute it in a depth-first manner, right? Depth-first execution doesn't have a lot of parallelism, right? So what we can do is use a transformation that's a lot like point blocking to create a different execution schedule for that code. I'm going to execute the code in a breadth-first manner instead of a depth-first manner. So I've got this BFS foo now that operates over blocks of tasks instead of the current task. And then for each block of the task, this looks a lot like point blocking, I check to see if it's a base case, run the base case if I need to. Otherwise, I add the children tasks to the next block, the next level of the execution. So I'm basically going to execute this tree level by level, right? There's a lot of like Silk schedulers that do similar things. We're just doing this as a code transformation, right? Because we're doing this all sequentially. So now I'm executing the tree level by level, and I again have this nice dense for loop that I could potentially vectorize. Right? And that's the first step. The first step is, hey, by doing this, I've basically taken that task parallelism, and by executing it level by level, I've exposed a bunch of these dense data parallel for loops that I can vectorize. But there's a problem here, which is that, hey, those dense data parallel for loops get bigger and bigger and bigger and bigger. If you execute a computation tree level by level, the size of one of these task blocks is proportional to the width of the tree, which is huge potentially, right? Potentially exponential. I really don't want to do that. Okay? So I want to control space usage, and the way that I'm going to do this is by realizing that I don't have to keep doing this breadth-first execution. Maybe at some point I can take that block of tasks and switch back to executing in depth-first mode. Stop generating new work. So for example, I can take that block of tasks and just run the original code, right? So for each block task in the block of tasks, if it's the base case, run the base case. Otherwise, do your left child, do your right child. Go back and execute depth first, right? I stop making the task block bigger and bigger and bigger. And then we see something interesting, which is that inner for loop there is a repeated recursive execution. It looks just like the kinds of tree traversals that we can apply point blocking to. So what if we apply point blocking to this code? Right, this is my depth first code. I get something that looks like this. So now I've got a depth first version of my execution, which says for each task, check to see if it's a base case and run the base case. Otherwise, add the left task to a block, add the right task to a block, and continue. And then when you're done, run all of the left children and run all of the right children. I'm going to run these task blocks. Run all of the left children, then run all of the right children. And what this does is it basically prevents the task blocks from getting any bigger. My new task blocks are at most the size of my original task blocks, so I can control space explosion. And then I can play other games, and I can, for example, switch back to breadth first execution if the task blocks get too small. So I can sort of bounce back and forth between executing level by level and executing in this block depth first way. But at all times, I have these nice dense for loops that I can vectorize. Okay, so really quickly, because I'm running out of time, we applied this transformation to a bunch of recursive task parallel programs. We vectorized them through various combinations of auto-vectorization and intrinsics. It turns out that even ICC is sometimes not so great about doing if conversion and things like that when you want to. So we do some of this with intrinsics. On average, we get a speed up of 2.58x. Not every part of the program, not every part of these codes can be vectorized, so we're only targeting some portions of it. But we get an average speed up of 2.58x, and actually our maximum speed up is about 9x for the beefier programs, basically. So, in conclusion, irregular algorithms are really fertile ground for locality and parallelism opportunities. It's a space that not as many people have been looking at, but it's a space that contains a lot of really important applications, really interesting applications. And our perspective in our group is that to really make headway here, we want to consider these applications at the right level of abstraction. Because when we abstract away the behavior of these applications, we can expose the sort of more regular behavior that these irregular applications have. And so that informs the transformations that we want to do, it informs the correctness criteria that we want to do, it informs the way we reason about locality effects. And so when we're done, we're able to do all sorts of transformations to improve locality, improve parallelism, improve vectorization across a bunch of irregular applications that normally compilers don't do a lot with. And I want to end by just acknowledging there's really all this work is done by a whole bunch of students, so I want to thank them, I want to thank my collaborators and the funding agencies because they pay the bills. Thank you.
Do you have a sense for your vectorized tree transformation, how quickly you hit that point of like the diminishing returns? So you did really good on 4 SIMD lanes, but what about 8 or 32?
Okay, so the question was for the vectorized tree transformations, do you sort of hit a point of diminishing returns or making your SIMD lane, having more and more SIMD lanes so things get worse? It is absolutely the case that the more SIMD lanes you have, the larger block size you need in order to sort of keep those SIMD lanes full. What we didn't really talk about is that even with all of these sorting transformations, the blocks that you run tend to have to be somewhere on the order of maybe 4 times to 8 times larger than the number of SIMD lanes you have in order to get good performance. What's going to basically cause problems for you? So you can basically always find a block that is big enough to get good SIMD performance, meaning that, to get good SIMD efficiency. I can always choose larger and larger and larger blocks and make sure I keep my SIMD lanes happy. The problem is that as my blocks get larger and larger, I'm more likely to get blocks that are too big to fit in cache. And that's truly what the sort of limiting factor here is. So yeah, I think that as you get to larger, if you move to larger SIMD widths without making your caches larger, for example, on maybe something like the Xeon Phi, you might run into trouble. We haven't actually explored that, but yeah, I think you would run into some diminishing returns. Essentially, what we're trying to do is make sure that our blocks can fit in cache. And so all of the rest of this is basically about tolerating the use of smaller blocks so that our blocks still fit in cache. As your SIMD width gets bigger, you're going to need bigger blocks, and so you'll run into that wall.
So the crop transformation, are they done manually or automatically?
So the question about is whether the code transformations are done manually or automatically. They're actually automatic. I probably should have put all the links up. All of the code transformations I talked about here, point blocking, traversal splicing, the transformations we do for vectorization, they're all automatic. The code is actually all available from my website. What is not always automatic is some of the vectorization stuff. So as I said, ICC does a reasonably good job, and in the paper where we explored the tree traversal vectorization, we found that ICC was able to get us maybe about 80% of the performance if we just sort of turned it loose. But in places where there were times when we had to sort of go in and insert intrinsics and things like that to squeeze out the last bit of performance from vectorization. So the transformations that are automatic are the transformations that restructure the code. The vectorization part is basically just using standard vectorization techniques, if conversion, masking, all those sorts of things. Compilers are better or worse at that depending on a whole number of factors.
And also the that first to right first, which is basically kind of a bit like Nestle.
That's right. That's right.
And then you basically have the same problem Nestle has, and you solve it by photoshopping it.
That's correct. That's correct.
Quite nice.
That's right.
Solution.
But yeah, so those transformations are also automatic, and those are the code is available for those as well.
This is based on sort of mutable data structures?
This is based on, that's right. So this is based on mutable data structures. For many of the applications, the primary data structure, meaning the tree, doesn't change, right? So in Barnes-Hut, one iteration of Barnes-Hut n-body traversal, right, the n-body tree traversal code, the tree doesn't change. It changes from one iteration to the next. Part of the reason that we went off and did the tree dependence analysis work is that we want to be able to optimize places where the tree changes as well. And we can transform and improve the locality of places where I'm building the tree. So the tree is actually changing. So in Barnes-Hut, the way that the octree is built is it's built in a top-down manner. I basically start with the original node, and as I insert points, I split nodes into their sort of 8 constituent children. As it turns out that I've got too many points in a particular node. So that kind of top-down tree traversal is clearly mutating the tree, and we were able to use our framework to show that you can actually still apply point blocking there and still get performance benefits from point blocking. Right. So the question here is about the tool chain. Okay, so first of all, the tool chain is a horrific mishmash of a bunch of different frameworks because some stuff we did in Java, some stuff we did in C, different students did it in different ways. So the original transformations, the point blocking and traversal splicing transformations that we developed in Java use JASTAD. So JASTAD is just this Java source-to-source transformation framework. It's really just a compiler framework, but we use it to do source-to-source transformations. The restrictions there are actually fairly light. We don't want to be in the business of doing a lot of shape analysis and things like that, so we ask that the programmers kind of tell us that the data structure they're looking at is a tree. Our hope is that it's easier for a programmer to tell you that it's a tree than for the programmer to prove that all the transformations are going to be correct. So we do ask, point blocking, traversal splicing, and tree dependence analysis are all written in JASTAD, and they do have this restriction where we kind of just, because we didn't want to do a lot of other analysis, we have the programmer tell us that this is a tree, and we have the programmer say, this is the method that I want you to mess with. For the most part, the transformations are robust in the sense that they will just refuse to transform code that doesn't look like a tree traversal. And what we expect when we are looking for tree traversals is essentially just a recursive traversal of the recursive data structure that you've identified as a tree. If you have that, and if the traversals are pre-order, so we obviously want to restrict that, or remove that restriction. If the traversals are pre-order, we'll do the transformations for you. The C++ frameworks are much more finicky and brittle, and they mostly require that you write the code to look like the Java frameworks already expected them to look like, and then they will transform the code. If you give it some malformed code, I actually don't know what would happen. It's research infrastructure.
The question's a bit speculative.
Sure.
If you have a traversal where you're doing a great deal of work within the inner loop, so you've got a lot of potentially you've got a lot of dependencies that may limit your ability to do reordering of traversals. Have you got any experience of where it's then actually more efficient to refactor the code in multiple traversals and carry forward some kind of indication of work? Because that would always be contradictory to the usual practice of trying to do loop fusion. So does that technique actually make it better to split apart multiple traversals in order to optimize the use of SIMD lanes, for example?
Okay, so let me make sure I understand the question, and also by way of repeating the question. So typically when you want to do things like loop fusion, you're basically saying I want to take a bunch of work and put it together. But if I have these traversals where within any individual method I'm doing lots of work, there's lots of dependencies, and potentially it restricts the way that I can reorder traversals, and it absolutely can. Could you split apart traversals? I think the answer is yes. We have not played around with that so much. I mean, traversal splicing, in some sense, what it's doing is it's breaking traversals up. And then it is doing some reordering, which you may or may not be able to do. But we have certainly found a lot of benefit in breaking these traversals up into smaller pieces, because when you break them up, the intuition is basically this. When I break something up into a smaller piece, when I take a traversal and I break it up into smaller pieces, the smaller the piece is, the more regular that looks. Right? The smaller the piece is, the less random stuff I have time to do. So as you break things up into smaller and smaller pieces, you can get better and better SIMD efficiency and things like that. And that's certainly what we have seen. We have not tried pushing it too far in that direction. I think it would be interesting to see what would happen if you do. I don't know if that answered the question or not. All right, so this is a nice leading question on TRX part. So the question was, do you have anything to say about GPUs? And the answer is yes, we do have something to say about GPUs. So I left one piece of work out of the talk, which is similar experiences about mapping tree traversals, irregular programs to GPUs instead of SIMD units. And GPUs are both nicer and more painful in a couple of ways. They're nicer in the sense that all of the painful stuff that we have to do about getting ICC to vectorize our codes, that goes away with GPUs, because the GPU SIMT hardware does all of the masking for you. It does all of the scatter gather operations for you. It will just run your code in a vectorized way if you give it a data parallel loop. So we don't have to worry about any of that stuff. What has turned out, so the work that we did about mapping these programs to GPUs, this was in supercomputing in 2013. we noticed two things. So the first thing was that GPUs are not so great at recursion. They can actually do recursion. If you've got function calls in your kernels, they'll do the function calls. If you've got recursion in your kernels, it will all sort of work. And it will work kind of the way you expect it to. It's just really slow. So the first thing that we did was we did a bunch of transformations to the code to essentially